In this video, I will solve the practice test problems. The first problem is a transport equation, which is a first order linear PDE, and we are required to solve this problem using Laplace transform. Now, to apply the Laplace transform, we have two variables, x and t. We need to determine which variables we choose to apply the transform. Now, because when t equal to 0, ux0 is 0, so we should apply the Laplace transform with respect to t. The reason is that the property of Laplace transform. So applying the Laplace transform to a functional, to a derivative of a functional equals s times the Laplace transform applied to f minus f0. Therefore, if f0 is 0, then this term disappears. So this is why we choose to do this for the variable t, because when t equal to 0, u is 0. Okay, so now we applied, as we said, Laplace transform with respect to t, and we denote by capital U the Laplace transform of our small u, the unknown function. Then our PDE becomes this ODE. Okay. The ut equal to what? Laplace transform applying to ut equals to su. We should minus u0, ux0, but this is 0. ux0 is 0, therefore we do not have ux0, simply su. So the equation, after applying Laplace transform, the equation becomes su plus ux divided by 1 plus x equals to 0. So simplified this equation, we get our equation here. Okay, this is easy. Now, apply the Laplace transform to the boundary condition when x equal to 0. What we get? We get capital U when x equal to 0 equals the Laplace transform of small u 0t. But small u 0t is 1. So this equals the Laplace transform applying to the constant function 1. The result is 1 over s. So using this, consider this as a first order linear ODE, whose unknown function is capital U, whose variable is x. Then we can solve this and obtain the solution is given by this formula. Now, having obtained the Laplace transform of our solution u, to get the u, we simply apply the inverse transform. So our small u equals to the inverse transform of our capital U. But the capital U is different when x is 0 and when x is positive. So we consider the case that x is positive first. Okay, then the Laplace inverse transform for capital U when x is positive equals to the for this step we simply copy our u to here. Now the result of this Laplace transform is the Laplace transform of 1 over Laplace inverse transform of 1 over s switched by a distance x times x plus 2 over 2. Look at the Laplace transform table in our textbook. We have Laplace inverse transform of g e to the minus a s equals to small g t minus a. Okay, now that is this property. So in our case, capital G is 1 over s, and the small a here is simply our x times x plus 2 divided by 2. Okay, so this function, I make a mistake. This is not t minus a. This depends on two cases. It's 0 if t less than a, and if t not less than a, the result is g minus a. So simply translate the function gt by a distance a. Okay. So using this result, you can check in the textbook, in the Laplace transform table in our textbook. So now in our case, capital G is 1 over s, and the small g is therefore the constant function 1. So using this result, we see that the inverse transform of 1 over s times this exponential equals the translation of our inverse transform of our capital G, that is 1 over s. That is our small g is 1. The inverse transform of 1 over s is 1, as we know here. Then this means the value of 1, the value of the constant function at this value, okay, for t greater than or not or equal to this number. Then when t less than this, x plus 2 divided by 2, the result is 0. So eventually it becomes 1 and 0. So why this is 1? Maybe some of you will be confused. Why this is 1? This 1 follows from this. As I said, this means the value of the constant function 1 at this argument. Okay, this is the variable. Now this expression means the value of the constant function 1 at this variable. But because this 1 is a constant function, therefore for every variable the value of the function simply is 1. That is why we have 1 here. So we have already solved the problem. We already find that our u when x is positive. But we still need to solve the case that x is 0. Now when x is 0, from the expression of u here, we see that when x is 0, capital U is simply 1 over s. So x is 0, then capital U is 1 over s. And the small u is the inverse transform of 1 over s, which is the constant function 1. So our solution is given by this expression. Our solution is given by this expression. This expression is valid for positive x, and u equal to 1 is for when x equal to 0. Okay, so we also need to describe the shock wave front along which the discontinuity between the initial and boundary condition propagates. Now, so to do this, we need to establish the coordinate system. Here is x, here is t. Then this curve, t equal to 2, t equal to x times x plus 2 divided by 2 is crucial for this. So this is a parabola, okay, passing through the origin. So this is a parabola. This is the curve. T equal to x plus 2 divided by 2. Now our condition and the boundary condition is discontinuous. Why? Look at the origin. The u is not continuous at origin, because when your x approaching to 0, sorry, when your point xt approaching to 0 along the t-axis, that is when x is 0. When x is 0, u is 1 here. U is constantly 1 on the t-axis. But when u is 0 on the x-axis by the initial condition, so u is 0. So this means that our u is discontinued at the origin. But this discontinued, and from the expression of our solution, we also know that u is 1 above this red curve, and u is 0 below this red curve. Okay, so it is also discontinuous along this curve. So the discontinuity at the beginning is at the origin, but as time goes on, the discontinuity move along this curve and propagate to infinity. Okay, so this is the shock wave front. That is this curve. Okay, so that is our first problem. Now let's go to the next problem. The next problem is wave equation, semi-infinite, because x is from 0 to infinity. Okay, t is time. So this is semi-infinite stream wave equation, and this is initial displacement and initial velocity, initial condition. Also, we have boundary condition. This is a kind of Newman boundary condition at the origin. So when x equal to 0, the derivative of our solution u when x equal to 0 is given by t sine 7 sine t. Okay, that is the initial condition. Of course, our solution is a bounded solution. Okay, if we're removing this bounded requirement, the solution might be not unique. Okay, you have more than one solution. You don't know which one is the one you want. Okay, so let's solve this problem, and we are required to solve this using Laplace transform. Again, we need to determine which variables Laplace transform applied. Now we see that the initial condition means that when t equal to 0, u is 0, and the derivative is also 0. So it is good to apply the Laplace transform with respect to t. Our property, let's go back to the property. Our property of Laplace transform, you see, Laplace transform applying to f double prime equals to s square Laplace transform applying to f minus sf0 then minus f prime 0. Okay, because of this property, look at our exact equation. Since if you apply with respect to t, then when t equal to 0, this term is 0, and the derivative is also 0. Therefore, L utt equals to s square Lu minus sux0 minus utx0. But by the initial condition, both this and this are 0. So the Laplace transform of utt is simply s square times the Laplace transform of u. Of course, the Laplace, we denote by the capital U, the Laplace transform of our solution u, then the left-hand side of the equation becomes s square Lu, that is s square capital U. And the right-hand side of the equation is u double, the second order derivative of u with respect to x. So consider as a parameter and x as the variables. Then this is a second ordered linear ODE. The initial condition is what? For capital U, we're applying the Laplace transform to the boundary condition, Newman boundary condition at x equal to 0. We obtained the partial derivative of capital U with respect to x. When x equal to 0, this is the Laplace transform of 7 sine t. That is 7 times the Laplace transform of t. From the table, you know that the Laplace transform of sine t is 1 over s squared plus 1. So this gives us the one of the initial condition of the capital U. Okay, so we have a ODE, second order ODE for u. And we also know the derivative of u with respect to x equal to 0. So this does not consist. This do not consist of initial value problem, because to get initial value problem, you still need to know the value of capital U itself when x equal to 0. We don't know this information. Okay, but the bounded assumption will help us. Anyway, we don't care about this missing information for capital U at x equal to 0. We simply solve this ODE. Now, the general solution of this ODE is C1 e to the sx plus C2 e to the minus sx. This is easy. Now, because the solution is bounded, because small u is bounded, capital U is also bounded. Therefore, C1 has to be 0. Otherwise, if C1 is not 0, multiplying this exponential term, when x goes to infinity, this term will blow up. Therefore, C1 must be 0. So our u is simply c2. C1 is 0, so C1 this term we can erase this term. Okay, we don't need to consider C1. Now our initial condition is capital U, the derivative of capital U with respect to x at x equal to 0. So to apply this initial condition, we need to compute capital U. Now we need to compute the derivative of capital U with respect to x. So this is also easy. This gives us this expression. Now using the initial condition, we see that let x equal to 0. Let x equal to 0. The right hand side of the expression of capital Ux is just minus s c2. But we also know that when x equal to 0, ux equals to 7 divided by s squared plus 1. So we see that this equals 7 s squared plus 1. So from this we can solve c2. c2 is given by this formula. Having obtained c2, our u is what? Our u is here. C1 is 0. This is our capital U. Now we already know C2. Having obtained the C2, we can give the expression of capital U. So we decompose C2 in terms of the so-called simple fluctuations. Okay, that is the term downstairs at most is a quadratic term. In the original expression, this is a cubic term, so we can decompose in terms of this. This is the technique we learned in calculating the indefinite integral in calculus 1. And also when we study ODE, we also need this skill. So we have no time to repeat this here. Anyway, writing C2 in this form, then our capital U is simply both of these two terms multiplying the e to the minus sx, that is here. Remember our C1 is 0. Okay. Now to continue our discussion, I copy the capital U to the next page. That is here. Now now the solution is the Laplace inverse transform of capital U. So our small u is simply this. What's this? This is the Laplace inverse transform of these two functions. Okay, these two functions. Using the linearity of Laplace inverse transform, the multiple, the constant 7 can move out of the operation. Then this also equals to Laplace transform, the difference of the Laplace inverse transform of these two terms. Okay, because Laplace inverse transform is linear. Now each term can be computed. The first term is cosine xt. What I mean this notation? Now, I had mentioned this notation. Given a function f from 0 to infinity, and given a number a positive, we can define a new function fa, also from 0 to infinity. Okay. Fa, the value of fa at t equals to what? Equals to f t minus a if t is greater or equal to a, and 0 if t is less than a. That is the function fa. This is my notation, but I think this notation is a perfect notation to denote this function. The graph. Okay, the graph of these two functions, suppose your f is here, then your fa. Suppose a is here, then your fa, the graph is here. Translating the graph of f to a distance a, give you the graph of this function fa. Now, in our solution, this cosine xt means that translate cosine t. When f is cosine t, when f is cosine t, our fa is just our cosine xt. Okay. Now, why this is true? This is also obtained from the table of Laplace transform. In the table, and in the previous problem, we have already used this property. The Laplace inverse transform of e to the minus as times capital G equals to G small a. That is, G small a is the function we just talked about. G small a t is gt minus a when t not less than a, and 0 when t less than a. Okay, so this is the property in the of Laplace transform. You can check it in the table in our textbook. Well, for the second term, it is similarly. You can consider this e to the minus sx as you can apply this property applying to the case that g is 1 over s. Then we know that the inverse, the corresponding small g is the constant function 1. Therefore, applying this property again, you need to translate your constant function 1 by a distant x. Okay, here the the x in the exponential is simply the a here. Okay, note that our Laplace transform is applied with respect to t, the inverse transform with respect to s. Okay, that is why we have this. But this is not very concrete. We using the definition of GA here, we can write the right hand side of our solution in a more comfortable form. That is what? That is what's this GA? GA here is can also be denoted by GAT equal to HT minus A, GT minus A. You can also write this in this way, because the H function is the heaven-set function. H function is 1 if t greater or equal to A, and 0 if t less than A. So using the heaven-set function, this translate function, that is our GA here, can be written as the multiplication of two usual functions. One of them is the original g, the other is the heaven-set function h. So you can also write it in this way. Similarly, for the 7, so for the 1x term, 1x term is the g is constant function 1, therefore we don't need to write it. Okay, so this can also be given by using the depending on the t greater or equal to x and the t less than x. So when t greater or equal to x, the h function is 1, therefore the result is 7 cosine t minus x minus 7. And when t less than x, the result is 0. Okay, that is the solution of our problem. Now for this solution, what can we say? U equals to 7 cosine t minus x minus 7 if t not less than x, and 0 if t is less than x. What can we say about this problem? Well, our problem, where is our problem? Our problem is here. Okay, we are required to find the region on the Tx plane where u is 0. Okay, so to do this, we need to first we establish the coordinate system. So the solution when t greater than x and less than, this is x. When t greater or equal to x and t less than x, the expression for u is different. Therefore, the line t equal to x is crucial. So we draw the line t equal to x. Then we see that u is 0 below this line, and u is 7 cosine t minus x minus 7 above this line. Okay, so the answer for this reason is that that is the reason where t is 0 is simply the reason below this line. Okay, so this is the second problem. Now let's go to the next problem. The next problem is a Laplace equation, uxx plus uyy equals to 0. We are required to solve this problem using using the method of emerge. Method of emerge means that depending on the boundary condition, you make an even extension with respect to one variable or odd extension, so that it becomes here is a semi-infinite problem. Okay, therefore you need to extend to become a totally infinite problem. Then you can use Laplace Fourier transform to solve the totally infinite problem. As you know, the Fourier transform of a function equals to the integral e to the minus I alpha x ux dx. The integral is from minus infinity to infinity. Therefore, the function should be defined over the whole real axis. But now our u for both variable x and y are defined only semi-infinite. So you need to apply the Fourier transform, you need to extend the function u with respect to x or y, depending on your boundary condition. Now let's check the boundary condition. Here we have ux 0, y equal to 0. So maybe we should draw the coordinate system first. So x, y. So we have ux 0, y equal to 0. This condition tells us that because of this condition, we need to make even extension with respect to x. Our u is only defined on the here for positive x. Of course, y is also positive. U is defined in this reason. We need to extend the u. We need to consider make an even extension for this u with respect to x, so that u is defined over the upper half plane. Okay, and therefore the other boundary condition where y is 0. Sorry, y is 0 should be y is 0 is the value of u. This boundary condition when y equal to 0 and x positive is defined here. That is this function I denoted by small f. This small f should also be, because our u is even with respect to x, so this f here should also be extended to the negative axis. Altogether, give with the even extension of the small f, that is 2e to the minus x to the 5. After even extension, we obtain a function capital F defined on the whole x-axis. Okay, then we obtain a problem on the upper half plane, which we can solve using Fourier transform. Okay, that is how to solve this problem. Now, as I said, let capital F be even extension of this small f. Small f is this function. Okay, 2 times exponential function. Then we consider this problem on the upper half plane. Now x is valid through the whole real numbers. Okay, so this is a problem on the upper half plane, which the capital F as the boundary value prescribed on the x-axis. That is the boundary of the upper half plane. Okay, we solve this problem, and in our lecture, using Fourier transform, we have solved this problem. The solution is the so-called Poisson integral formula. We know that the small v is given by this formula. So restricting this v satisfies the PDE. This v satisfies this PDE, means that its restriction to the first quadrant also satisfies our PDE for u. Okay, and also this v satisfies this boundary condition. That is our v equal capital F on the x-axis. Okay, in particular, It also equal to f on the positive x-axis, but that is small f. On the positive x-axis, capital F is simply small f. This means that our V also satisfies this condition. Okay, therefore this V is satisfies our PDE, satisfies our boundary condition, one of our boundary condition. We need to check that it also satisfies the third boundary condition. What's this? What's this? Okay, we need to check that it also satisfies this boundary condition. This should be checked. And also the V is expressed in terms of capital F. Therefore, we also need to replace this capital F in terms of our small f. Okay, that is how to deal with this V. So first we will express this V in terms of small f. Now, because capital F is the even extension of our small f, so we split the integral from minus infinity to infinity to be two integrals. One is from 0 to positive infinity. In this interval, capital F just equal to small f. Therefore, this integral from 0 to infinity can be written using small f. The other integral is from minus infinity to 0. But in this reason, capital F, because capital F is even extension of small f, so capital F xi equals to small f minus xi. Okay, so this is the first step. In the next step, the first term already good, we don't need to do anything. The second term, we make a changing variable. How to change? Changing the variable, let minus xi equal to eta. Then this can be written as eta, and this is plus eta. But d eta is minus d xi. So the d xi here is minus d eta. And when xi equal to minus infinity, eta equals to positive infinity. When xi equal to 0, eta equal to 0. But the minus sign here, we can use the minus sign to reverse the upper and lower limit of the integral. Therefore, originally you integrating for eta from positive infinity to 0, which the minus sign, it can be written as integral integrating from 0 to infinity. Okay, that is our result in terms of f. But this is still too complicated because you have two terms. We want to combine these two terms. So to continue our discussion, I copy the last line to the next page. That is here. So we can replace the. We can replace this integral. We can replace this integral. Sorry. This integral, the xi, the eta, the variable of integral by replacing it by xi. Then we see that we can both integral have a common term f xi. We can move this out of this, and then what limit the two fractions we add them together. So this equality is true. So this is the better expression for our v. That is the expression for v. In terms of small f. The original expression for v is originally the v is expressed in terms of capital F. But since our problem there is no capital F, so after our this argument, we have already expressed the v in terms of small f. So this is the solution in terms of f. But as I mentioned, we still need to check that can we have u, if we let u to be the restriction of v at the region x positive, okay? Can we have u x 0 y equal to 0? Can we have this problem, this property? If this is true, then our u as the restriction of v for positive x, it gives us a solution of our problem. Okay, if this is not true, then this is not a solution to our problem. So we need to check whether this is true. Now, as we did for this kind of problem, we need to compute Vx 0y. We need to compute this. If this is 0, then ux 0y is 0. Therefore, the restriction of v for positive x, that is the u, is the solution of our problem. Now, to check the Vx, we need to take derivative of v with respect to x. Of course, it is not good. It is not good to take derivative with respect to x in this expression because you have two terms to compute. This will be complicated. Instead, we check this using the original expression. Using this expression, okay? We're using this expression. Now remember this expression. I will go to the next page. So using the expression, since v is the integral capital F divided by this, therefore the partial derivative of v with respect to x is partial derivative taken here. But you can switch the order of derivative and the integration, derivation and integration. So this partial derivative can be moved inside the integration. Therefore, we have this result. Okay, that is the expression for capital the partial derivative of v with respect to x. Now, so you have to compute this derivative. The result is that the downstairs term you square, then taking derivative with respect to x. Okay, that is easy. Computing the partial derivative. This computation have nothing to do with Cauchy. Cauchy can be treated as a constant. Therefore, all these are constants, and y is also constant. So this is easy to compute, right? So from this, what can we say? What we want to check is whether when this is 0, when x is 0. Now, when x is 0, you see that this part is an odd function of Cauchy. The variable is Cauchy. This is odd because the downstairs term is even. There is a square here. The upstairs term is odd, obviously odd. Okay, and the capital F Cauchy is even. Okay, capital F Cauchy is even. Therefore, the total integrand is odd. Even function times odd function, this is odd. So an odd function integrating from minus infinity to infinity give you 0, right? The blue one is odd, the red one is even. Their multiplication is odd. Then the integral is 0. So this verified our conclusion. So Vx 0, y is 0. Therefore, the restriction to positive x is solution of our semi-infinite problem. Okay, this method we have applied several examples in the lectures. Okay, now let's go to the next problem. This is a so-called reaction diffusion problem. This is very like the heat equation, but there is an additional term minus u here. Okay, that is the difference. That is the difference which to the heat equation. Okay, we have a heat equation, infinite heat equation, and also we have initial when t equal to 0, initial value problem condition. Therefore, we can solve this problem. Of course, we have never solved the reaction diffusion problem, but using Fourier transform, this is the method is similar to what we did for heat equation. So we applied Fourier transform with respect to x, because x is the only infinite variable. T is only semi-infinite. Fourier transform can only applied for infinite variables. So we have to taking Fourier transform with respect to x. Then the left hand side, the left hand side is the left hand side, we use capital U to denote the Fourier transform of small u. Therefore, the Fourier transform of ut equal capital ut. So the left hand side is capital ut. The right hand side, we know that Fourier transform of uxx equals to minus alpha square capital U, using the property of Fourier transform. Okay, so that is why we have alpha square capital U. And the last term, the second term on the right hand side is U, respectively. After Fourier transform, it is capital U. So this is the ODE we obtained by applying Fourier transform to our PDE. This is an ODE whose unknown function is capital U and whose variables is small t. Also, so this is the ODE. We write this ODE in a better form. Okay. Now the initial condition should also be should also be a Fourier transform. Okay. Now the Fourier transform of uxt0 is simply capital U when t equal to 0. We know that your function is small xt. After Fourier transform, you have capital U alpha t. But when t equal to 0, when t equal to 0, that is u alpha 0 equals to the Fourier transform of small u x0 when t equal to 0. Okay, but this is just the Fourier transform of x divided by 1 plus x to 4. Okay, I use this hat notation to denote Fourier transform. This is a very convenient notation. Now, we don't need to compute the Fourier transform of this precise function. We simply, because eventually we will need to apply the inverse transform. So we don't, unless necessary, we don't compute this transform. Instead, we simply use a notation. It seems that capital U0 is a good notation for this. We use this capital U0 to denote the Fourier transform of this function. Okay, now this gives us an initial value problem for first ordered linear homogeneous ODE. It is easy to see that the solution is given by U0 times this expressional function. Okay, therefore our small u is the inverse transform of this capital U. Okay, that is the inverse transform of this function. But in this function, we can move something out of the operation. Why? Because Fourier transform are related with the variable alpha and x. Our Fourier transform has nothing to do with t. Therefore this term, this is what? This is e to the minus t e to the minus 5 alpha squared t. And the e to the minus t part has nothing to do with the variables related to the transform. So it can be treated as a constant. Therefore, since the Fourier inverse transform is linear, the constant e to the minus t can move out of the operation of the transform. Okay? So we simply need to compute the Fourier inverse transform of this. But the inverse transform of the multiplication of two functions equals to the convolution of their inverse. So u0 times exponential inverse equals to u0 inverse convolution with the exponential inverse up to a constant 1 over square root of 2 pi. Okay. Now the inverse of u0, since u0 is the Fourier transform of x divided by 1 plus x4, so the inverse of u0 is simply this function. So the u0 inverse is this function, and the exponential inverse is this function. This is a Gauss function, Gauss density function. Okay, we know that the inverse of this function is also of the same form, but the relating constants should be careful. Anyway, this is a no result, or you can check from the table of Fourier transform. Okay, so then the last step is to write this solution express this convolution in terms of integration. So by definition, the convolution of these two functions, equals to the integral of their multiple, but one of them, the variable x, should be replaced by x minus c. Okay, that is the last step. Is simply the definition of convolution. Okay, so this is this problem. Our last problem is a wave equation, infinite wave equation, and we have initial displacement and initial velocity. Okay, so of course we need to take Fourier transform to with respect to x, but before doing that we split this problem in two problems. By the principle of superposition, if V is a solution of this problem we have the same PDE, the same initial displacement, but the initial velocity is 0. Then W is the other problem. PDE is the same, but the initial displacement is 0, and the initial velocity is given as that of U. Okay, so we decompose our original problem into two problems, V and the W problem. Now, from the principle of superposition, the sum of the solution of these two problems is the solution of our original problem, as you can check. For example, so UTT equal VTT plus WTT, but VTT is 25 VXX and the WTT is 25 WXX. Okay, therefore their sum is 25. VXX plus WXX is V plus WXX, that is 25 UXX. So this U satisfies our PDE. For the initial condition, you see UX0 is VX0 plus WX0, but WX0 is 0, so we only have VX0, which is x1 plus x squared. Okay, so the sum satisfies the initial displacement. Similarly, you can check that the sum satisfies the initial velocity. So the sum is the solution of our problem. So to solve this complicated problem, we only need to solve these two simpler problems. These two simpler problems can be solved using Fourier transform. So for V, we apply the Fourier transform with respect to x. The PDE becomes UTT equals minus 25 alpha square Vx V. Okay, then moving the 25 alpha square V to the left hand side, we obtain this ODE. And correspondingly, the initial displacement, here the capital V is the Fourier transform of small v. So when t equal to 0, capital V equals to the Fourier transform of Vx0. So maybe we have repeated this computation several times, but maybe some of you need that is V alpha 0 equals to the Fourier transform of small v x0. Okay, using this result, we have this. Okay, And also the this function, we don't need to compute the Fourier transform of this function. We denote it by V0. Okay. Similarly, for the initial displacement, of course, for the initial velocity, since it's 0, its Fourier transform is also 0. Again, we know that Vt equals to the Fourier transform of small vt. In particular, when t equal to 0, then this is 0, because Vt is 0 when t equal to 0. Okay, so this is the initial value problem for a second ordered linear ODE, which can be solved. Now we use the complex exponential function to express the solution of this problem. Otherwise, we could not compute the Fourier inverse transform. Therefore, we use the complex function. Now, to continue our computation, I copied this result to the next page. Okay, capital V is given here. Then our small v is the Fourier inverse transform of this capital V. Okay, now using the linear property of Fourier inverse transform, this can be written as the average of the Fourier inverse transform of these two functions. Okay, this function and this function. V0 times this. Okay, then because we have a half times multiplying a half here, therefore the result is given by half of the sum of these two inverse transform. Okay, now this two inverse transform is computable by the property of a Fourier inverse transform. By the property of a Fourier transform. Maybe I need to find this for you. Let me check our. No, maybe. Yes, long ago. Yes, this property. This property. F applying to F minus C equals to the exponent of minus IC alpha F alpha. Maybe I should write it here, which means that you apply the inverse transform to both sides. Apply the inverse transform to both sides. You get what? You get Fourier inverse transform of e to the minus IC alpha equals the left hand side is simply F alpha minus C. Okay? You applied Fourier transform and then Fourier inverse transform. These two applications cancel. You only have your function. Okay? So we need this result. We write it here. Okay. Now let's go back to our computation. So the compare this two. Compare our V0 term. In this case, the C is what? The C is for the first. The C is phi t. Okay, C is phi t. So the Fourier inverse transform of this is the value of the Fourier transform of capital V0. That is we denoted by small v0, evaluated at. Sorry, this should be x. Evaluated at x minus phi c. Okay. Similarly, for the second term, the c is minus phi t. Therefore, the inverse of this multiplication equals to the inverse of V0, that is our small V0 again, x minus phi t, that is x plus phi t. So this is the solution. Okay. Now V0 is what? V0 is V0 is this function x1 plus x to the 6. Okay, sorry, x1 plus x squared. That is V0. Okay, so replacing the, remember our V0 x is x1 plus x squared. Replacing the x here by x minus phi t and x plus phi t give us this V. This V is the solution. This V is the solution of our PDE for small v. Okay, so we want to solve our problem. We decompose into two problems. Then one of them has been solved. We need to solve the other to get W. Then their sum u plus v plus w is our solution. Okay, now let's solve the second problem. To solve the second problem, that is the W problem, we apply Fourier transform with respect to x, and we get the same ODE. Because W and V satisfies the same PDE, of course, after Fourier transform, the resulting ODE are the same. Okay, but for the initial condition, because for our W, the initial displacement is 0. The initial velocity is not 0 here. Therefore, correspondingly, after a Fourier transform, the Fourier transform of small w we denoted by capital W will satisfy this condition: initial displacement and initial velocity. Of course, we don't need to compute the Fourier transform of this initial displacement. We simply denote it by capital W 0. Okay, then this can be solved. This time we don't use the complex exponential. We simply use sine and cosine to express our solution for this initial value problem. As you can check, so the general solution of this ODE can be written as linear combination of sine phi alpha t and cosine phi alpha t. Then using the initial condition, you can determine that the coefficient, okay, of the linear combination. It turns out that this W is the solution of this initial value problem for ODE. Now, W, the small w, that is the solution of our WPDE here. Okay, this W will be the Fourier inverse transform of our capital W. That is this function. Now, to compute the Fourier transform of this function, we to apply the sum property of a Fourier inverse transform, we rewrite the sine phi alpha t divided by phi alpha. We add a coefficient here. Correspondingly, we need to balance the coefficients. Okay, and the phi here, since this is linear, the inverse transform is linear, this phi can move out of the operation, okay, to get this result. Now I copy this to the next page here. Now the multiplication, the inverse transform of the multiplication equals to the convolution of their inverse. Okay, so the inverse of course, this convolution need to divide it by square root of 2 pi. Okay. Now, W0, the inverse of W0, we denote it by small W0. which is simply this function. This function is small w0. Okay, small w0 applying Fourier transform give us capital W0. Well, this is what small w0 is. Now, yes, that is this small w0. Now, convolution with the Fourier inverse transform of this function. And checking the table of Fourier transform, you can find that this inverse is the characteristic function of this interval. I have mentioned several times, given a set chi a x equals to what? Equals to 1 if x belongs to a, otherwise it is 0. This function is called the characteristic function of the set A. Now this notation here is the characteristic function of the interval. Okay, so this is easy. That is the graph of this function. The graph of this function is when x belongs to the interval minus phi t to phi t, the value is 1. When x is not belongs to the interval, the value is 0. Therefore, this is the function. Okay. Now we need to write this convolution as an integral. By the definition of convolution, the convolution of W0 and this chi equals to Wx minus xc times the value of chi xc, then integrating from minus infinity to infinity with respect to xc. Okay, that is the definition of convolution. The time comes from simplifying the coefficient in front of this convolution. Okay, so now, of course, because when xc not belongs to, if xc not belongs to minus phi t to phi t, then chi minus phi t, the value of chi at such xc is 0. So this integral can be rewritten as an integral from minus phi t to phi t. And in this interval, the chi, the characteristic function, is 1. So this disappears. In this interval, this is 1. Therefore, it disappears from the integrand. Okay? So, then this is what? This step, we apply the changing variable. We let x minus c to be eta. Then c is x minus, simply changing variable, very easy, right? Let this back as a function eta. Then this integral become, maybe I should clear everything. Yes, let this be eta. Then this integral become eta. Okay, very easy. Now using the form of our W0 is x divided by 1 plus x to 6. Therefore, this is W. So we have obtained the solution for the W PDE. Then, as we said before, their sum v plus w. This is v we computed earlier. Then w is simply this integral. Then this gives the solution of our wave equation. Okay, so this gives the solution of our wave equation, which non-zero initial displacement and non-zero initial velocity. Now the solution is given by this formula. Okay, so this is the last problem in our practice test. Okay.